view the data and you can select the factors, you can combine it with other impact factors of other impact categories and get an overall picture of your results, including water use, water consumption, and its reference is described in the paper. So the midpoint factor, it's mainly based on this water stress index. That's the map I've shown before, and it's on watershed level. All the factors are on watershed level. And we have endpoint damage factors which are compatible with eco-indicator 99 method. So that means you can also have aggregated results, including water use, and define how much is the share of the total impact from your water consumption. So we have the 3 areas of protection. We have impact pathways to human health, ecosystem quality, and resource depletion. So this is many data behind that. We have many calculation steps, and I want just to show you at this point different maps. So it's not mainly about the content, but it's about, we have some maps on raster data, so it's pixel maps. We have data provided on watershed level, and at the end we had to combine it. So it's more about that you see how these different layers interact, and that different steps have different high factors and low factors in different regions. So it shows also if you would aggregate everything on country level, you lose a lot of information along the way, and finally you end up with completely different factors, and it's at the end also a diluted result. So if we have the midpoint impact factors, that's the water stress index. So this is on watershed level, and just to view what's in there, so we have the water scarcity maps. It looks quite similar. It's also on watershed data, but then there's another factor included there, and it's the precipitation variability. This is the raster data, so that means it's on pixel level, and for each point we have calculated, and we calculated then everything together, and at the end we finally aggregate it on watershed level based on the consumed water. So if we have the aggregated damage factor, we have this map, which includes the human health map. This human health map, you see, it's not much in the developed world, and this is mainly because we have a human health factor. We have the human development index, which is on country level. So after having developed the method, we went back and said, okay, we have a lot of regions which are very populated, like China, India, Russia, and Brazil. It's like almost 1/3 of the global population. So we felt like it's not so good to have one value for all these big countries. So we went back to the national statistic and selected regional human development factors or indices to calculate the human development factor. Now this human development factor, you see in the States, you have impact to human health, even you don't have any impact within the States, but the impact is downstream in Mexico, where you have in the southern rivers, you use up water, and in the States there would be no impact, but as Mexico is much lower development index, there will be impact on human health, at least according to the method. So if you talk about ecosystem quality, this is also on watershed level, because we also need to consider the upstream downstream effects. But if we look at the input data, it's all on raster data, so we have vulnerability to water shortage modeled for each pixel, each cell on the map, and we have the precipitation, which is as well available on relatively high resolution. The last point is the resource depletion. This is just on watershed level, taking the water stress index, and that's it. So what can we learn from that? It's a lot of different scales, and it's a lot of aggregation at the end. So we need a lot of calculation on high resolution and then aggregate it at the end. So we need to combine the individual states of the art, so we don't need to aggregate everything before to watershed level, combine together, but we need to have, for each factor, we need to see which is the best resolution available. It's always on data availability, so we can't choose, we can't go out and measure everything, but just pick the one which is most suitable. So, as I explained, if you identify a need for higher spatial resolution for certain points or certain aspects, we need to go back and maybe we can find there some better data which might improve the result without having a large additional effort to do. So the main answer here is that we have to aggregate as late as possible. And that's also if we combine the impact factors with the inventory, because if we generate country average impact factors, this should, in the optimal case, be based on where is generally a process in the inventory taking the water from. So if you know that cotton production in the States is mainly in the south, so we should also have the country average impact factor for cotton production in the States based on the impact factors in the south of the States and not in the north of the States, because there is no water use there. So this is the example. We have an inventory of water consumption. We calculate on pixel level and aggregate it on watershed level. We have the impact factors on watershed level, and this gets multiplied. At the end, we have the production per watershed, so we see that the production is not at the same location as the impact. While we had the impact rather in the west, the highest production are more in the central east. And then at the end, we can aggregate, like this is the impact multiplied by the production. So we see that if we take the overall American cotton production, the main impact is in these areas, while we have like almost no impact in the eastern part. So if we now want to have an average impact factor of cotton production, we get the results from here, and we can exclude the damage factors in the eastern part. Now the conclusions, we have to calculate, always is a repetition, but that's really my point. We have to calculate on the highest resolution possible. We need to define the inventory flow as locally as possible, and if, as it is in reality, often not possible to have very specific data, we need to have the aggregated factors based on the high spatial resolution, and also for the background data, we need the national average data to have it in the supply chain management. So that means if we have the foreground data, we can adopt the local data, we can look up, but if you have the background data, we need to have generic inventories where we apply the average factor for each process. I mean, that's a huge work which has to be done, but then we can have, for the whole background data, we can have average impact factors applied, and if I pick just corn in the US, it will give me the average impact of corn production or of cotton production in the US. So that means for all this process, it would be good to have a country average, which can then be used for background data if you have a regionalized LCA, which is working also with regionalized LCI data, which might be on country level only. So the final point is to show the uncertainties, because uncertainties are widely neglected. So it's really the uncertainties of the inventory and the impact assessment, because mainly impact assessment, that's something I'm planning to do, so I'm working on it, but for the inventory it's a completely different point, and also to have the problem addressed with the wrong or right location. So really to be able to have not only the uncertainty of the data in the point, but also the uncertainty of picking the wrong data, so the wrong impact factor. So that's like an uncertainty in the space and not only the value at a specific point. And that's leading somehow to a trade-off between precision and accuracy. So we increase the precision, but the accuracy might gain some additional problems. So that's it, and I hope you have some interesting questions for me.